Bismillahirrahmanirrahim. Assalamu alaikum. This is lecture number 14. In this lecture, we will program all those examples that we did in lecture number 13 in assembly language. The programs or the topics that we will do inside this lecture are the flow control instructions, and the examples of flow control instructions will be covered here. Before continuing this lecture, I would like to review the previous lecture, what we did in our previous lecture. In that lecture, we studied about the clock cycle. This is the complete clock cycle, like one clock cycle starting from here to here. And then we also know about the instruction cycle. That instruction cycle has multiple stages or sections: instruction fetch, instruction decode, operand fetch, and the instruction execution and the write back. So there are different registers which are involved in this whole process. For example, we have instruction pointer, or we have a program counter. So instruction pointer or program counter, these two registers have the address of the next instruction that is to be executed. So these two, this register depends on the architecture. This register has different names. So program counter has the address, and from this address we fetch instruction inside the instruction pointer or inside the instruction register, are called the IR register. So we fetch instruction from this address, move that instruction inside the IR, then instruction decode process continues. After instruction decode process, CPU determines that either do we have to fetch operands or not. In case if we have operands, we will fetch those operands, and then the third or fourth step of instruction execution will happen. Otherwise, the direct instruction execution will happen, and the results will be written back either to the memory or to the registers. So also we discuss about the jump instruction. This jump instruction is unconditional jump to any label that's usually within the same procedure or within the program and so on. So what happens, there are flow control instructions which determine the flow of the logic or the program flow. For example, as we discussed in our previous lecture, our program has multiple instructions inside the code segment. So sometimes we transfer control from, normally program control follows this direction from upward to downward. So first instruction will be executed, then next instruction, then third, and so on. But sometimes we have instructions that conditional instructions or unconditional instruction that can transfer the program control somewhere else, here or maybe from forward jump or backward jump and so on. So these type of jumps or these type of flows or these type of flow controls are divided into two, either conditional and unconditional program control instructions or flow control instructions. So jump is one of the instruction that is unconditional jump, unconditional flow control instruction. So usually it jump to the target or the address. So we will see how this happens inside the program. So the target is usually the label. So this label shows the address or the offset. So address of the program, the statement which is written here or whatsoever, and so on. So instruction pointer or the program counter has this address to continue the flow of control of program control or program execution. Then we studied or we discussed about the loop instruction. This loop instruction creates the counting loop, or this is the conditional control instruction. So this instruction what will happen, definitely it has same format, almost syntax is same, but at the back end what will happen, we assign some value to ECX, and ECX in every loop or in every iteration, this ECX is decremented. We decrement 1 from the ECX, and again value of that result, this complete result, is again sent back, stored inside the ECX. Now the next thing that we check here, either if ECX is not equal to 0, if ECX is not equal to 0, then we jump to the address, this address or the label. If ECX is equal to 0, then jump will not happen or will not be performed, and program will follow the normal execution. Now in our previous example, previous lecture, we discussed about these instructions, like this move AX, its address is like 00, offset address is 000, all these zeros, and this instruction is 4-byte instruction, this one is 4-byte instruction, this one is 5-byte instruction, this one is the 3-byte instruction, and 2-byte instruction, so on. For example, suppose. So what will happen here, you can see starting address is 000, and then after these 4 bytes, the next instruction's starting address is 04. After all these 5 consecutive memory locations or consecutive bytes that are assigned to this instruction, the next instruction start from the 0009 offset or this address. So this offset or address depends which memory access mode we are using, either real or protected and so on. So here 9 is the starting location, and it occupies, this instruction occupies 3 bytes. So the next instruction's starting address is C. So label is assigned here, or the label shows this offset. So this label shows this offset 0009. So when this instruction is being executed here, so the program counter already has this value. Program counter already has this value. For example, the value is 0E. So offset value is calculated based on the current value of the program counter. So for example, this is -5 in hexadecimal. Actually, this is 2's complement, a representation in hexadecimal. So program counter is added with this computed calculated offset and so on. So it performs jump based on the condition that either the value of ECX is equal to 0 or not. If it is not equal to 0, then jump, otherwise it will just return back, or it will follow the normal sequential flow. Now there was some example about the nested loops. So for the nested loops means loops inside the loops. There's inner loop and there are some outer loops and so on. So here you can see we have inner loop, then we have the outer loop. One thing we have to keep in our mind, if we are using nested loops, then before starting a loop we assign some value to the ECX. So what will happen, for example, here ECX is 100, and we do something, do some calculation and so on this ECX. We transfer this value, we do some calculations here, and before starting the inner loop, what we should have to do is to save this value, current value of ECX, so that when we exit or when this loop completes its execution, then we can continue from where we have left inside the outer loop. So we first save ECX or the value of this counter, and then we start with the new counter value. When this counter will over, then again we will perform the outer loop and so on. So before going to perform the outer loop, again we have to get the value from this, the value which we have saved and so on. So in this lecture we will do all the instructions that we did in the previous lecture, examples in the assembly language, and now let's enjoy the assembly. So just start with the Microsoft Professional. We just create new project, this new project is Visual C++ and console application. The name of this project is lecture number 14, example 001. So where we want to store somewhere. We have created a new directory. You can see on desktop, CSC lecture number 14. Okay, so we select this folder, and this is the new project. So next, we don't need anything, we need only empty project. Okay, so here we have empty project. First, as usual, build optimization or these properties. So build customization, you have to select MASM, and source files, we add source file, new item. So any file you can select. For example, if we select code, and for example if we say C++ or something, so we write, we don't need C++, we need assembly. So what we do, we say example 001 a.asm. so this will be the assembly language program. And the next thing that we have to do, we have to set the properties, Microsoft Assembler, and include path, that will be C drive, MASM 32, and we have the include directory and so on. Okay, so this is our new project, and now what we are going to do is we just copy the skeleton of the program. This is the skeleton of the program, so we just copy this one and paste it here in our main program. So you can see this is our program. Now what we want to do is we want to do some jump instruction and see how this jump instruction executes. Now, for example, inside data we say variable 1 byte. Variable 1 is a byte, and its value is 10h, 20h, 30h, and for example 40h, and so on. Okay, now in the code segment, what we write here, for example, move ax or al, comma, variable 1, move or perform. Okay, now for example here we say this is the L1 or label 1 or whatever you can call it. For example, L1 colon, and then we write add al, comma, variable 1 plus 1. Okay, now here we say or here we write jump somewhere else, whatsoever. We can draw some map here. This is L2. Okay, so L2 is add al, comma, variable 1 plus 2. Okay, and after this one we say we will perform some jump, and here is L3, for example. So L3 is here. So before we are going to jump GMP to L2, When we will jump to L2, we will jump to here L1 and jump to L3. Now you can see the program logic. Our code starts with the move AL comma variable 1, so the first element will be moved to the AL. Then we jump to L2, so it will jump here to this label and it will add AL with the second element. Then it will jump, for example, we can make it like easier like this one. So it will add the second element with the AL, then jump to the L1. It will come here and jump second, third element, and then jump to L3, and L3 is the last instruction that will be executed. That is a system call or routine to exit from the program. So for example, we can save this one. We can build solution. Just I want to make this one to see. Okay, so build, clean build, rebuild the solution. So here you can see rebuild all, so succeeded, 0 failed, and so on. I just step by step execute. So okay, now here is the registers. Here are all the registers. Now I will just show you the output, then we will see how actually program executes. Now for example, initially 10 is moved to the AL, so this part is 10, and next one is we jumped here. Now 20 has been added because this instruction has executed. Now we have to jump here. Then the third instruction has been third element has been added, and we jump at the end, and program ends. Now we can see what happens inside the program. Before going to do that, I will show you one thing which will be more interesting for you. Now when we perform this execution, what registers do we have to follow? We have to follow instruction pointer and also the instruction pointer register, and also we have to see what are the addresses assigned to this whole program. So I just built again to make sure that there is no error and so on. Still okay, so it's okay. Now I just step and debug, step over. Now just right click here. When you right click here, just press the go to disassembly. So here you can see view options, show code bytes, show source code, show code bytes, and so on. Okay, now I just hide these options, show addresses and show symbol names. Okay, I just symbol names and so on. I just remove this one. Now here, these are the registers. Now I will move towards the first instruction that is to be executed here. So it will start from here. Jump L2. Jump L2 is JMP, and this instruction is EB08. EB08, and you can see L2 is 2B100F. This is the address or offset where it will jump. L2, if you can see here, L2, this is 2B100F. 2B100F, this is the address where we will perform jump. So here jump instruction is EB08. Okay, this is for the jump, and L2 is this address, so it will jump to this address. So these, if I just hide show the source code, I just hide source code, code bytes, show addresses, show symbol names. Okay, so here I just show symbol names, show code bytes, and I just hide the source code. Here you can see this is jump to L2, this is add instruction, 8AL byte pointer VAL2. So VAL2 is VAL plus 2. This is the address from where we will fetch this operand. So this is the calculated address after this VAR plus 2 and so on. Then there is a jump EB08. This is the jump code for the jump instruction EB08, and again we have jumped to L1, so EBF0, and then we have this address where we will perform jump, and then L3. After L3 you can see for the exit call exit process 0. So first it will push 0, then it will call this one exit process. So exit process is stored 2B1026. So this is the exit process or the procedure which perform the exit operation. So can you see here now, if I perform this is the source file from here to here, complete source file. Now here you can see initial instruction is at 2B1005. 2B1005. This is the initial address for the initial instruction. Next instruction is 2B1007. 2B1007. Now 2B1007 is the next instruction which perform the aid operation, and this is the starting address. How many bytes are there? 1, 2, 3, 4, 5 and 6 bytes. There are 6 bytes. So this instruction contains the address also. So this is part of the address or the operand from where we fetch the operand. Then we have this opcode and the pointer for the variable and so on. So this is address. So address is like here 4-byte address and so on. So we have also 02 and 05 for the aid AL. We have 0 to 05 and this address. So this whole instruction is 4 plus 2, 6-byte instruction. It means this instruction is 2-byte instruction. 2-byte instruction, and then we have the 6-byte instruction and also 2-byte instruction. 6 plus 2, how many bytes? 8 bytes. So EB is jump, and now this is called the offset. So from L1, from here we are going performing jump. After how many bytes we want to perform jumps is 8 bytes. So this will directly go towards here to the L2. Similarly, if we want to perform backward jumps, and this is the negative offset, so EB and negative offset and so on. And if we perform the jump towards the L3, so L3 is after how many? 1, 2, 3, 4, 5 and 6, 7 and 8 bytes. So these two instructions are occupy 8 bytes. After 8 bytes we have this offset. When we add this offset, we will come here up to 2B107. Now if I want to execute, for example, F10, this is the first instruction. So the first instruction has been executed. If I want to, I just source code only. So I can just stop this one, just execute normally. Now here what we have to do, we have to see how this will execute. I think it's better we just go to assembly and view the options like show code bytes. I think there's no need to show code bytes, only the addresses. Show addresses and label names. Okay, so addresses and label names are sufficient. Right now we are executing the instruction F10. Now we are here, jump L2. We have first move instruction. So this is the move instruction which is inside this one, so it's not here shown. So this is jump L2. So it will perform jump L2, but before performing jump L2, AL is moved with 1 0, the first element of our array. You can see instruction pointer is currently at this point, BA1005, and where it will move to 0BA100F. So when this instruction will execute, perform execution, so this will be the new address where it will move. For example, you can see here the instruction pointer. Just note this value. So this is the value which was shown here. It has been added or updated in instruction pointer, because now this instruction at 00BA100F, which is the add AL and byte and so on, from this address we will get the value for the second element and add. Still, this instruction did not perform any execution right now. However, you can see the instruction pointer holds this address, so it means instruction pointer holds the address of the instruction that is to be executed. जब भी execute होना शुरू हो जाएगी, then instruction pointer will hold next instruction or other instruction. For example, अभी मैं इसको अगर execute करूँ तो next instruction हमारी होगी jump instruction. Now this is the next instruction which will be executed, and instruction pointer has this value 00BA1015. So this is the next instruction to be executed. अब इसके बाद कौन सी instruction execute होगी? This should be 0BA1007. It's L1. So this is L1. It has the address, so we want to jump there. If I press this one, then it will be updated with 00BA1007. So now we are going to add third element. After adding, so jump will happen to 0BA1017 hexadecimal. That is the instruction which we call to exit from the program. So this is the instruction or the value that will be inside. So you will see 017 will be added here. So now we just come here, but still we did not execute. I did not press F10. So if I will press F10, this instruction will execute and it will exit from the. So you can see first push has been performed and now it has exit from the program. So we saw that we can transfer control inside the program by using labels and unconditional jump instruction. Now this jump instruction was quite easy, and these labels, actually these labels, now you know that these labels, when we write inside the jump, they show the addresses, they represent the addresses of those instructions where these labels are written. इस इंस्ट्रक्शन को जो भी कोड सेगमेंट में या कोड सेक्शन में जो भी इसको एड्रेस असाइन होगी, चाहे ये इंस्ट्रक्शन 4 बाइट्स की हो, 5 बाइट्स की हो, 6 बाइट्स की हो, तो उसकी जो इनिशियल एड्रेस होगी वो जहाँ पे ये स्टोर हुएगी 6 बाइट इंस्ट्रक्शन. सो दिस लेबल विल शो और रिप्रेजेंट और होल्ड्स द एड्रेस, उसकी स्टार्टिंग एड्रेस को. सो आई थिंक नाउ this is unconditional jump, so we perform only the addition of these 3 elements. Now we will move toward the nested loop. Before that one, we will start the loop instruction. Now I think we have to save this one. We just save this one and close this project, file, and then close solution and so on. We just open a new project, the same one. This is the lecture number 14 and example 002. So we will create this directory, and next empty project, customization as MASM, and we just add new item, whatsoever the item is, C++ file, anything, but we will write the name here, example 002 and .asm, so it will be assembly program. We just added, right click, see the properties. So either there is include path or not, because this is the main thing that we have to do again and again. MESM 32 and include directory, and okay, there's a method you can, once you can do that one, and then you can forget all about this whole process. So in this program, or in this example, I just copy the skeleton of the whole program and then paste it here. So now we are going to do the loops, loop statement, that is the conditional loop. So for example, variable 2 is a byte. I can say it's a word 100 h20, okay, is the one, or I can write it 0010 comma 0020 0030 hexadecimal, and then 40, and so on. So this, there are 1 2 3 4, I can add another one is the 0050 hexadecimal, and it depends whatsoever you want, how many elements you want to add. Now we are going to start with the this example. For example, if I say move ax comma 0 and move ECX. So ECX is a counter variable which will automatically be decremented. It will be decremented again every time the loop has been taken, or loop is being executed. So what will happen if the loop or the value of ECX is not equal to 0? It will loop or jump again to the target or to the level. If ECX is equal to 0, then it will follow the normal execution. So what will happen here? You can see ECX is equal, for example, 5, and I want to write here the add AX comma CX, and then loop LX or LP1. LP1 is the label name, so I put LP1 here, LP1 and colon. So this is the label. Okay, control, just save this one. Okay, this one is okay. Maybe I can make it EAX ECX. So you can visualize the whole process or whole register contents. I just save this one, build solution, so you can see whether the build was successful or not. So it was successful. If I execute, so this EAX will be 0. So this is the instruction that will be executed, 0. And now ECX will be moved with ECX value. Value inside this ECX will be 5. Now we will add EAX and ECX. So initially EAX was 0, and now 5 has been added. Hexadecimal value 5 has been added. Now we will jump. Now you can see that when we will perform this, execute this jump, so ECX has been decremented automatically. Can you see here? The value of ECX is, when this instruction will execute, it will decrement first and then check the condition. If the condition is true or false, then it will take the decision. What is the condition? Condition is that if ECX is not equal to 0, then jump to the target, or jump to this address, or jump to this label, because this label shows the address. Okay, so again, if I press F10, so 4 and 9 or 4 and 5, they have been added. This jump will calculate decrement. So when ECX is equal to 1, this 1 will be added. Now this is the time when ECX value is equal to 1. Now when this instruction will execute, it will decrement. It has decremented, and now you can see this ECX is value of ECX is equal to 0. So when it is 0, it will not go again back to this loop and so on. It will just return back to the normal flow. And you saw this, you can perform this loop by incrementing this, decrementing this counter automatically. Okay, now what we are going to do is we want to have the nested loops, for example. Before nested loops, we want to do the addition program to add all the elements. For example, if I add this one should be 0, 1. Okay. And then now we want to add all these elements. What will happen if we add all these elements? How we can add? Now we know that we have seen so many. We did all these statements like the the offset is operator and direct operator, pointer operator, and other operators. So we will use, for example, operators like offset, move, the ed, for example, the EDI. This is the register. EDI is moved with the offset of the variable 2, and the next instruction that we want to perform is we want to have the value of ECX is equal to the length of variable 2. So now we know that the value inside the ECX is 1, 2, 3, 4, and 5. So it will automatically calculate the length. And then the next thing that we want to do is we want to have EAX. In case if we want to have EAX, for example, or AX, move AX, comma 0. So we want to put sum here, the total. We want to put total here. Total is inside this one. This will serve as a counter. And this will give us the base address, or the starting address. Okay, now what we are going to do here, we want to have, before that one, I want to clear the contents of EAX or the register to see either it's going to perform addition properly or not. So we have got this one. So here we have to add the elements. For example, how we can add the elements? We know that we can perform the AX EDI. So this will get the value from that indirect addressing mode, and it will get the value. Now we have to add EDI, comma the type of variable 2. So variable 2 type will be added here, and then nothing else. So just we save this one. We just build the solution. So you can see the solution here. So it is 1 succeeded and 0 failed and 0 up to date and skipped and so on. So we just execute this one. Initial is exclusive or EAX. EAX means so clear the contents of EAX. Now the next thing that will happen, that EDI this is the EDI register that will hold the address, or destination index register, or this index register will hold the address of the variable 2. Okay, now ECX is length of variable 2. So ECX, you can see here, ECX is equal to 5. Automatically it will be updated with the current, based on the number of elements, whatsoever the number of elements are there. So now if you want to have move AX with 0, it doesn't matter because we already cleared the contents of AX. So there will be nothing will happen here, it will be again 0. Okay, now we are going to perform addition. AX will be performed with EDI. So EDI shows this one, 001. So it has been added here. Then we are going to add EDI with type. Type is equal to, because the size, the type of this one is word. Word is 2 bytes. So EDI will be incremented. So EDI will be incremented or added to. So this you can see, previously it was 1C4000. Now it is 1C4002. So we have to jump again because the ECX is equal to 5. And now when this instruction will execute, it will decrement and check the condition. So it will be 4. So it will continue adding all these elements. You can see. So 001 has been added with this one, then this one. So after that, this is the this one is 1. So this is the complete addition for all this, and the final loop is going to over. So for example, if I want to make this one like here, I want to add the number of elements, 0, 1, 0, 0 in hexadecimal, and I want to repeat this one again. Okay, I want to repeat this whole process. Number of elements are more than 5. So whatsoever the size of this array is, we don't care. It will automatically calculate. So this is the more flexible program compared to the previous program that we did in lecture number 13. Not lecture number 13, lecture number 12, I think. So in lecture number 12, we also did the sum of this array by using indirect addressing and so on. So if the whole for adding each element, we have to add separate add instructions. So now we have reduced the size of the program. Just we have to save and we have to build. It's successful, then execute. It's okay. So the output, you can see. So when we add all these elements, this one, so output should be 2222 in hexadecimal, and end of the program. So this is why it is 22, because 0001 is added with 0010 in hexadecimal, 0100 in hexadecimal, 100. So when we add them, all these 4 elements, they will give us 1111 hexadecimal, 4 ones, and so on. So then the next time when we add all those elements again, it will give you 2222 hexadecimal. So this was the example where you saw that where we saw that we can perform the all these loops without having the these conditional loops, and it simplified the array sum program. Now what we are going to do here is save this one, and now we will have the we will try to have nested loops, for example. Now if we have nested loops, what we have to do, as we discussed, in case of nested loops, I just save this program and close this one and close solution, new project. This is the lecture number 0, lecture number 14, and its example is 03 is the name of the, this is Win32 console. So Visual C Win32 console application, and empty project, and finish this one. Customization. Okay, add this item, any file, C file or something whatsoever you can select, but we just write name here. Example 003a.asm. Don't forget to write ASM. If you forget, it will, whatsoever the file type you will select, it will give the extension or assign the extension to this file. So it will not be the assembly file. And if it is not the assembly file, when you right click, when you see the properties, you will not see here Microsoft Assembler. So okay, Imagine 32 and these include directory and so on. Okay, this is done. Now we just copy the skeleton. Okay, so this is our program. I want to give you one more example for the question that I asked in my previous previous lectures. For example, if I want to write move EAX comma 0, move ECX comma 0, and add EAX comma ECX, and here I say loop LP3 for example. So LP3 is the label. Okay, now as I asked in my previous lecture, what will be the number of iterations that this loop will execute? You can check it by yourself here. So we can experimentally check this one. Build. Okay, so build is successful. Now we just run this one. Here you can see we are going to start with the EAX. So EAX will be 0, and then we are going to have next instruction ECX is 0. So ECX was already 0. Now we are going to add EX and ECX, so 0 is equal 0, so no problem. We just loop again. Now just see, when we loop here, this is FFF. It is not 0. The value is inside the ECX because this instruction just subtracts, or decrements 1 from the ECX first, and then check either it is equal to 0 or not. If not equal to 0, either it is negative, positive, it doesn't matter. If it is not equal to 0, then jump. Now it will jump for infinite times. You can see until and unless. So there are how many digits? 1, 2, 3, 4, and 8. So ECX is 32 bits. 2 raised to power 32 times it will continue. 2 raised to power 32 times. 32-bit ECX. So 2 raised to power 32 times it will continue its execution, and then you will be your program will be like almost you have to wait for a longer time to complete its execution. So you saw this example also. Now for example, if I want to do another example for the infinite loop, this is finite loop, even though this is also the finite loop example, because we know that 2 raised power 32 will end sometime, maybe after 1 hour or 2 hours, or maybe less than that one, or maybe within minutes, depends on the machine that you are using. But there is possibility that there can be infinite loop. How you can have infinite loop? For example, if I say ECX is equal to 5 or ECX is equal to 2, for example, and add EAX ECX increment ECX. Okay, now if I say increment ECX, then you should be very much careful. Why I am writing all this? Because before starting the nested loop example, I want to show you that we have to be very much careful when we use registers. You must know which register you are using and which register you have to modify, and which registers are available, which are automatically changed by the program, like the instruction pointer and other registers and so on. And for the loop automatically changes the ECX register. So be careful when you are using loop instruction. Then be careful that when you change the value of ECX. So this is the reason I want to show you the examples. So in this example, for example, this will be infinite loop. I just build this one. It's okay. Now initially EAX, it will be 0. Now ECX is equal to, and we just go to the here, add 2 has been added to EAX. Now we will just move to the next instruction, increment ECX is equal 3. This will decrement ECX. It will be 2. So this 2 will be added with the previous 2. So just continue. It will continue for infinite times. Whatsoever the number of times you want to execute, it will continue. You can see it will never stop. It become 3 and then 2, again 3 and 2, 3 and 2, increment, decrement, increment, decrement, and so on. So just try to avoid this type of situations. So now this was example for the infinite loops, and be careful which value you are going to assign to ECX when you use loop instruction in your program. Okay. Now before that one, or after that, after this example, we want to have the nested loop example. For example, if we want to have multiple loops, then what we have to do, we have to save the for example, counter 1 is the size of the double word. Double word is 32 bits because we want to store the value of ECX. If I want to store the value of ECX, then I have to have double word, because ECX is the 32-bit register, so I must have the double word. I don't know the value, so counter has no value right now, no assignment of any value. Okay, now what we are going to do here, we want to have multiple loops. Now there should be some logic in multiple loops. How we can do that one? First, in the outer loop, we want to assign some value to the EAX. In the inner loop, we want to subtract something from the inner loop, and so on. For example, if I say move EAX is equal to 0, and then move EAX is with 5 or 4, for example. Okay, so I just save this one, and then what I want to do here is okay, so move ECX to 3 times, our counter is equal to 3. Okay, and after this one, I want to have loop here. For example, LP1 is the outer loop, LP3 is the inner loop. So it's okay, this is outer loop. So before starting this outer loop should be on the next line, for example here. Okay, so what will happen, I want to add, or I want to in this loop, before coming to this loop, the next thing which I want to do here is move the counter 1, move counter 1 comma ECX. Okay, so ECX is been moved, and then here I want to perform the move ECX comma 4, and this will continue the loop. Okay, just let me write the this is inner loop, so I want to perform this inner loop here. How will I perform this inner loop? Here is the ECX is equal 4, so decrement EAX. Okay, decrement EX and loop L3. When it will complete execution, then move it will move before here or maybe here, so we want ECX comma counter 1, and then after that I say move EX comma 4 loop LP1. Okay, seems good. Let's build solution. Okay, successful. F10 step by step execution. Initially we moved 4 inside the EAX. Now what we are going to do, this is the outer loop, so we assign outer loop to the EAX. Then before going to continue this outer loop, we are entering into the inner loop, so we assign this value of outer loop here in the counter 1, and then we assign new value to EAX, and we perform decrementing. So now EAX, when last time it will perform, the value of EAX will be 0 because it is decrementing 4 times. It is decrementing 4 times from the EAX. Then it will start the next counter. So the upper counter was equal to 0. It was equal to 3. So we got the value again, and again what we are going to do, we are going to move 4 again to the EAX. Now the upper counter value is right now EAX is equal to, it will be saved, and inner counter will start. Inner counter will decrement 4 times from EAX, and again we will get the outer counter. So this is the logic is, the logic which I use here is, okay, what was the logic that I used here is very simple one. The logic is that I assign 4 to the EAX register, and what I do, I want to decrement it inside the inner loop, and when again I start the outer loop, I assign again 4, and I want to perform this whole process 3 times. So this is the outer loop. Outer loop 3 times, and here we assign 4 to, this is EAX, and so on. This is to save the counter, save outer loop counter, and then we start new counter. start the inner loop counter. Then this is the inner loop. This is the inner loop logic, whatsoever the logic you are going to perform inside the loop. Okay, then we have the loop condition and so on. So this is complete inner loop from here to here, and this is the outer loop. So outer loop starts from here and up to here. So here, retrieve the counter, retrieve outer loop counter, and test the condition. Assign new value to EX. EX and loop condition, outer loop condition. This is the outer loop condition. Okay, so this is the complete logic. Now you can understand, first we assign 4 toward the EX, then what we are going to do is we are going to perform decrementing 4 times or 4 times from that value inside the EX, and then again assign the value 4 and perform decrementing up to 0. For example, 4 times decrements. So third time again we assign the value sem and so on. Okay, sorry. This is the build is complete. So build solution is complete. I think yes. Okay. One is updated. So rebuild. It's okay. Okay, so just see here, EX is equal 4. Sorry, EX is equal 4, 3, 2, 1, 0. Again EX will be 4, 3, 2, 1, 0. Again EX will be 4, 3, 2, 1, and 0, and so on. Oh, sorry, it is started again. Sorry. So it should be 3 times. Decrement for the first time, decrement for the second time, so ECX was 3, then once it will continue, then again, so this is the, it assigns 4, so 3 times, but it assigns 4, it doesn't perform any decrement, so 3 times. So it just assigns 4. So I think we can move this logic here, maybe this one, instead of moving there. If I move this one up to this point here, then it will also be good idea, and we can reduce one instruction here. If I just remove this one, okay, so we don't need to have so we can minimize the code. You can see, I'm sure this will be this code will have the same output. F10. Okay, so 4 has been assigned, 3, 2, 1. 1 time has been decremented. Again 4 will be assigned, 2, 1, 0. Second time decremented. Third time assigned 4, 3, 2, 1, 0, and now exit from the program. So we have assigned 3 times the value 4 to EX, and 3 times it has been 4 times it has been decremented, and so on. So the value 4 was assigned to ECX and completely decremented 4 times, and it was made 0, and then again assigned, so it's okay. So this is the code for the inner loop and outer loop. The main purpose for this code was, or the example was, to use how you can use loops or nested loops inside loops. So before going to perform anything, for example, if you want to have another loop inside this loop, then be careful. What you have to do, you have to save two counters, because if we have loop 2 inside outside, for example, loop 2 is here, and if you want to perform anything and loop 3 is inside loop 2, then you have to have another logic. How many variables you want to define? For example, counter 1 is one variable. If you want to have multiple inner loops, then how you can do that one? The main thing is there will be the concept of stacks. We cannot have multiple loops, multiple variables to hold all this data. So we don't know that how many loops we want to use. So the best option is to have the another structured data structure, another data structure that holds all this data. So that should be the stack and so on. So that is another option, but you have to be careful. When you start a new loop, just try to store its counter, not only counter, but just try to store all the variables or all the registers that are being used inside the that loop. For example, here we use EAX, and we don't want to use EAX here, for example, but unfortunately this loop is modifying something in EAX, then the outer loop has nothing to do with inner loop or something. So just try to avoid that. If you don't want to use EAX, but EAX has been automatically been used here, so it will give you the wrong result. So just be careful to assign store registers or variables that you want to use in multiple loops or nested loops. So this was example for the loops and so on. So now we will conclude. So here inside this lecture, we saw that instruction execution, how instruction is being executed. For example, we saw that in disassembly we use the loops and all these and jumps, and we saw that how instruction is being executed. Instruction can be 3 byte, 4 byte, 1 byte, 2 byte, and so on. And there are some addresses they are assigned. When we use jump instruction, that is unconditional flow control instruction, so this jump instruction unconditionally transfer control to the target, and this target is nothing but the label. This label shows the address of the next address where program control or program counter or instruction pointer will means point out. So it was unconditional. Then we also saw when we disassemble the whole program that there is offset also with each opcode. For the jump, there was an offset like E8 or something. There was offset also, either positive offset or negative offset. So this offset is added with the main address and to calculate the new address where the program logic will be or control will be transferred. Then we discussed about loop instruction. This loop instruction is a conditional flow control instruction. This instruction utilizes EAX register as a counter. So first we have to assign some value, any value towards inside the ECX register. This ECX register is used as a counter. So first we have to assign some value to the ECX register, and then it will automatically decrement when the loop instruction is being executed. So the logic was, if ECX is not equal to 0, then loop instruction will jump to the target or the label, whatsoever you can call it. If ECX is equal to 0, then it will not jump. It will continue toward the next instruction, the sequential flow. And we saw that if we want to use ECX, then we should have to be very much careful to assign values. For example, if you assign 0, then this 0 will continue up to some certain number of times, that is a huge number of times, like 2 raised power 32 times and so on, it will continue that much number of time up roundabout. So just try to avoid. And another thing, there was a case for the infinite loop, like sometimes the loop instruction decrements, but we increment. Before decrement, we perform any instruction that automatically or that perform increment operation over ECX. So first, if you increment then decrement, there will be infinite loop. It will never end. Okay, so just try to avoid. And then in the end, we did we saw the example of the array sum example, and then we also saw the nested loop example. In nested loop example, the main logic was that first thing is you have to store counter for the outer loop, then start the inner loop. Otherwise, the logic will be wrong, because the same counter is being utilized by the inner loop. So ECX is the same counter which is being utilized by the loop instruction. So just try to avoid this type of situations. And in case of nested loops, if there are multiple loops inside the main outer loop, or there are other loops inside the inner loop, so you have to maintain all the counters, and you have to load all those counters when you exit from the inner loops. So this is end of the lecture number 14, and hope to see you inshallah in the next lecture. Till then, Allah Hafiz.